Hey there, and welcome to NASA's Curious Universe. Our universe is a wild and wonderful place, and in this show, NASA is your tour guide. Now, we've made more than 50 podcast episodes, taking you on adventures to the moon and Mars, inside of a black hole, and to some fascinating corners of our very own planet, Earth. Well, for the first time, we're coming to you in a video, too. So sit back, grab some popcorn, and enjoy this special bonus edition of NASA's Curious Universe. I'm Jacob Pinner. I'm one of the producers on the Curious Universe team, and today I get the pleasure of grilling Dr. Padi Boyd. Listeners of Curious Universe will recognize Padi. She's our host with the most. But what you might not know is that hosting this show is a small part of Padi's job. She's a full-time astrophysicist. She's been researching the cosmos for decades. Basically, she does all her own stunts. So, Padi, I've got tons of questions for you. And I think people who listen to this show are really going to enjoy getting to know the scientists behind the voice. So thank you so much for doing this, for sitting in the hot seat today. It's going to be fun.
I'm happy to do it, and I'm really looking forward to the conversation. So thank you, Jacob.
So you're a scientist. Why don't you run me through the basics of what you study? What are you interested in?
Great. So I study how light changes and what we can learn from those changes in light. And so that's called photometry. That's the technical word for light changing. And I study changes in light at wavelengths from X-ray to ultraviolet to optical to near infrared. So multi-wavelength photometry. And why is that so interesting? Mm-hmm. It's because we can learn so much about these objects that are really far from our hands here on Earth by just watching the patterns and then drawing some conclusions about what's driving those patterns. So we've been doing that for thousands of years as human beings. We looked at patterns in the sky and we figured out the calendar and the seasons, and then we figured out what the moon and the stars were doing and the sun, just by watching these patterns evolve and change and finding periodicities and then putting that together with a model of what's going on. So I use that concept to go even beyond our solar systems. How do we use changes in light to infer what's going on in things like stars, binaries with a black hole or neutron star in it, even like supermassive black holes at the centers of galaxies beyond the Milky Way.
That's some cool stuff.
It's really fun. And you got to go to space to get those extra wavelengths that we don't see with our eyes here on Earth.
Well, why don't you take me back to the beginning? Like, how did you get interested in space in the first place? And then how did you end up at NASA?
So I was a really big science fiction fan as a kid.
Oh, like what?
Well, I loved Star Trek.
Okay.
I just thought it was a beautiful concept for the future. You know, everyone working together and exploring the universe. So I was really drawn in by that, the science and the philosophy of it. But I also really liked reading books about science fiction.
Sure.
And I liked science programs. Like there was a show called Cosmos when I was a kid. That was Carl Sagan's show, and he was basically inviting everyone along on his cosmic journey. So that was like the first astronomer that I knew of. And that just kind of drew me into the field.
So one of your research interests now is exoplanets, planets that orbit other stars. And these days we know that there are a lot of them in our own galaxy, or a number of them.
Yeah.
But that's a pretty recent thing that we've found out. I'm wondering if you can just take me back to when you started studying exoplanets. What did we know about them at the time?
So when I first started out in the field, we didn't have any observations of planets beyond our solar system. We only knew about the planets in our own solar system, and then we were hopeful that there would be planets around other stars. There were good theoretical reasons to think that how our solar system formed is not special, and that when other stars formed, it would be through a similar process and that there might be planets there. But for a long time, it was feared that the planets are so small and they're so dark, they don't give off their own light, that it'd be virtually impossible to be able to detect them with the methods that we had. And then methods got better.
Wow.
And we were able to get signals higher and noise lower, and started using more telescopes, more telescope time, and looking for different types of patterns in the light. And that opened the field from something that was just basically a dream and a hope from when I started out to where we are today, a few decades later, where we now know there are more planets than stars in our galaxy.
Wow.
It's just an amazing result.
So how do NASA scientists actually find these exoplanets? I mean, like you said, they're small, they're far away. for a long time we thought that they would get drowned out. The light would get drowned out by the star that they orbit, right?
Totally. Yeah, so the sun is the light that you see from the sun. If you were to look at our solar system from outside, comparing that to, say, the reflected light on our planet Earth, it's 10 billion times brighter, the sun, versus the reflected light from the Earth. So you can see why that sounds like a hopeless problem.
Yeah.
But even though the planets are dark and small, they do impact their environment. They show signs of their existence even though you don't see them directly. So if they're massive like Jupiter, their gravity will impact the motion of the star, just like the star's gravity impacts the motion of the planet. It's kind of a yin-yang kind of thing.
Yeah,
They're both
so that
impacting
like the
each
planet
other.
is what, making the star wobble a little bit?
Exactly.
Wow.
Yes. So the star makes the planet orbit around it, but the planet also makes that star wobble around like their common center of mass. If you were to put them on a seesaw and have them balance out. So that was one way to look. Like that star moving towards us and away from us would imprint a signal and a pattern in the spectral data. So that's how some of the first planets were found, through this what we call radial velocity, or the wobble of the star. But also, if you're lined up really perfectly with that system, then when those planets move in front of the star, the planet, which is dark, will have this tiny dimming effect on the star. It'll block out a little bit of that light. And so there's photometry again. Let's look at how the light changes as a planet passes in front of a star. That's called the transit method. And that's how missions like Kepler and TESS find their planets.
Well, this kind of leads into what I was going to ask next, because we know that there's a lot of these planets, right? What else do we know about exoplanets, and how can we figure it out for these planets that, again, are small, far away, and can be difficult to detect?
So we're really just like scratching the surface right now. We're at the tip of the iceberg. Discovering the planet is like step one on this path. So there are ways to find out more about the nearest planets to us, because those are the brighter ones. But we need to special purpose design some instruments and some missions to really go after those faint signals and tell us what we want to know. It's like our biggest driving question right now is, how similar is our solar system to other solar systems out there? We know there are solar systems everywhere now.
Sure.
Well, how common is the process where life developed on our planet throughout the Milky Way?
Basically, like, are we special?
How special are we? I think one of the things we're learning is that every solar system is unique, just like every person is unique. But how unique, right? Like we're all breathing oxygen here, right? We all born, go through those teenage years, evolve. We want to be able to put our solar system in that same kind of context with the other solar systems out there. So the first questions we're interested in are like, what's the atmosphere like? Even the planets in our solar system have vastly different atmospheres. What about those planets around the other stars? Are they similar to Earth's atmosphere? What about Venus's atmosphere or Uranus's atmosphere? We don't see life on those planets, so that would say, well, maybe life's not there. What about water, clouds, weather, plate tectonics, magnetic fields, the things that we find so important to how Earth and life on Earth co-evolved?
Right.
How common are those situations out there? And that's the driving question for all of our technology going forward for exoplanet hunting.
Do you have a favorite exoplanet of the, again, very many that there are?
Yeah.
And if you do, can you tell me about it?
It's a really hard question because, like we were saying, they are all unique.
Right.
And if you're really curious, there's something to love about all of them. But I think the one that I find so excited that it's there is one called Proxima b.
Okay.
The nearest star to our sun is the Alpha Centauri system. And that's actually not just a single star. It's 3 stars. 2 of them are pretty bright, Alpha Centauri A and B, as we call them. And then there's a tinier star, very small compared to our sun, or Alpha Centauri A and B. But it's on an orbit around those 2 that brings it very close to, not very close, but closer to Earth than A and B. And so that's why that's called Proxima Centauri. It's the proximate one to us.
Okay.
We know that there's a planet around Proxima b, and we know it's in what we call the habitable zone or Goldilocks zone of that star, where the conditions are right that liquid water could exist on the surface.
Wow.
Could not.
I mean, the habitable for people zone?
Well, that's a very different question. But that's one
now
of the
I'm just
cool
like opening
things.
a whole door. And
These are great doors to open, though. You know what I mean? Like when we're starting to take that step through the door, the habitable zone is just a place around a star where if there were a source of water, it could stay liquid on the surface. It wouldn't all freeze up because you're too far away from the energy of the sun, and wouldn't all boil up because you're too close. It could stay liquid for a while. That's one condition, is having water on the surface. But that's definitely not the only condition. And so now we get to put sort of like the details on that question. What does it mean to be habitable? It's not just that zone. How do you have the other conditions where biology on the surface can actually flourish?
And I would have to think, given that we've learned so much about exoplanets in a pretty small amount of time, it seems like one of those fields where we're going to look up in another 25 years or something and say, man, back in the 2020s, we just didn't know what we didn't know.
I think so too. I mean, we're really just taking these first steps. So we're definitely going to be able to put a lot more information on these exoplanet systems as we go through this decade and the next. It's going to be a great time of explosive growth. It already is.
You know, I think for a lot of us who aren't scientists, like when we picture scientists wearing their lab coats looking through a microscope or a telescope or whatever, what we really picture is that eureka moment when you find a breakthrough or you discover something totally new or something like that.
Right.
But can you kind of take me into what that is actually like in reality? Like, is there one breakthrough or discovery or something that you can, tell me the story of and sort of put me in, like, what does it feel like and how does that actually happen?
Okay. So it's cool that you brought up that stereotype of like the lone scientist in the coat looking through the telescope or the microscope and having that moment of aha and everything changes.
The light bulb goes off.
The light bulb goes off. And that has definitely happened. But what we're seeing more and more is that science is done by teams of people. And that, each individual person brings their own unique strengths to a broader team, and that team working together can accomplish a huge amount. I think we tell that story so well in our Curious Universe episodes across the spectrum of what we do here at NASA. But the personal experience I had like that came with the Kepler mission. Kepler launched in the end of the first decade of the 2000s. And it was the first NASA mission that was specially designed to study exoplanets because they were so new.
Okay.
And at the time, we only knew of a couple hundred, and they weren't mostly found with the transit method. Kepler was meant to do photometry, like we were talking about before, on 100,000 stars at one time.
Wow.
Looking for those tiny dips or something that could be a dip. Those transit signals would first give us a signal in all that data that we would call, it had to cross this threshold to be interesting.
Okay.
So we called those threshold crossing events.
You said you're talking about 100,000
Yes.
planets or 100,000 stars?
It was an unprecedented computational task.
Okay.
100,000 stars, all that data coming down at once, and you're shoving it through this pipeline.
So you've like really got a fine-tooth comb to go through all this, right?
Yeah, that's a great analogy. And you're throwing most of that stuff away.
Huh.
You're really sifting through it to find the interesting stuff. And at the time Kepler was launched, we didn't know how common or rare exoplanets were. That was one of the big questions it was meant to answer. And we were kind of, worst case scenarioing it. What if Kepler didn't find any transiting planets, or very few, or showing that, planets just weren't very common in our galaxy? So we were ready for like a certain number of threshold crossing events. And when that first data slug comes down to the ground and goes through that pipeline and the team starts looking to see what they got, there's a lot more threshold crossing events than anybody expected. And so the first thing you think is like, oh, what did we do wrong, right? What's wrong with these programs? What could possibly be giving us these false positives, these threshold crossing events that shouldn't be there?
Right.
But at the same time, when you're looking for like, what could we have possibly done wrong? How do we explain this in making sure we're not making any mistakes? There was that ray of light at the same time. That maybe we're getting so many threshold crossing events because every star in this collection has a planetary system.
Wow.
And so the ones that we can't see transit are just the ones that aren't lined up for us. And the ones that are lined up, well, we're seeing threshold crossing events, or a huge proportion of them are showing us something like a threshold crossing event.
Right.
That's what the statistics were telling us from that very first moment.
Wow.
It could be that planets are everywhere. could be. And then just to see how those years, so that's the aha moment, right?
Yeah, that's a big
yeah.
aha moment.
Because you want to think, what could I be getting wrong?
Yeah.
Don't want to get this wrong.
Right.
So you're going to go through all that. And I think that's part of the aha moment too. Like, this can't really be right, is it? But then also that spark of, oh my goodness, what if
it is?
This is the best answer we could have ever hoped to get.
So, Padi, I have to ask you about something that I know about you that I think our listeners probably don't know about you. And that is that you're a great singer.
Thank you.
And you're in this band called the Chromatics that sings about space.
We do. So
I think the people need to know about this. Like, tell me about it. Tell me how you got started with it. Tell me about the Chromatics.
Okay. Sure. So we are an a cappella group. We don't sing with instruments. We sing music with our voices only. And we're a smaller a cappella group. So there's 6 of us. And so many of us come from NASA. We met through NASA. We met through a music and drama club. We accreted people who were space nerds just like us, even if they didn't work here. And so when we realized that many of us could sing things from our childhood, you know, like Schoolhouse Rock, or even commercials telling you like what's in a product. You could sing the song from your childhood and you remember exactly what you wanted to eat that day. We wanted to take that idea that music can really like bake those ideas into a mind and share some of the most exciting things about science, astronomy, telescopes, what's out there in the universe and how we know it, and put those in songs and share them with students and the general public. So that's what we do. We call that astrocappella because it's astronomy through a cappella. And we've been doing that for the whole time the group's been together. And we like to sing about missions. We like to sing about black holes and the habitable zone, the Goldilocks zone. We have a song about that. And we do activities for students that can be used in the classroom too. So sometimes we're working with teachers to get that content into a type of lesson plan that can be taught. And other times we're at museums just participating with any activities at a museum and working with the general public and singing to them.
It's like
singing songs of science.
That little spoonful of sugar that helps the astronomy go down, right?
Yeah, it's a good way to look at it.
All right, well, Padi, to cap off, I've got to ask you the question that we ask everyone we interview. This is something, again, that listeners may not know, but, you know, the name of the show is Curious Universe. We really try and follow that curiosity. So to end every single interview, we ask, Padi, what are you still curious about?
I am still curious about our model of the universe and how it began and how it's going to evolve.
Okay.
So
that's
a
big heady
question.
Thing to be curious about.
Yep, our whole universe.
Yeah.
But we're learning so much in the next couple years. You know, we've got JWST that's finally looking beyond what we were able to see with our telescopes before it came, finding those first galaxies and how evolved they are and what is that telling us about our models. But also, like, what's the Roman telescope going to tell us when it gets up and starts really interrogating things like dark matter and dark energy, parts of our universe that we know are so important to its evolution and its future that we can't really measure well yet. So I'm looking forward to answering those big questions in both directions, the beginning and the evolution, and how NASA's space missions are going to impact that.
All right, if you're up for it, I've got a lightning round of quick questions also to run through. This will be fun, I think.
I'm going to ask you the same ones.
Let's go.
All right.
First up, if you, Padi Boyd, could go to space, would you do it?
I would totally go to space. I think it's such a special experience. No hesitation. I'd love to see the Earth from that vantage point. I know it's life-changing for everybody who's been. I want to experience that myself. I think that'd be fantastic.
Okay, Star Wars or Star Trek?
Gotta say I'm a Star Trek fan more than Star Wars.
And even as a Star Wars person, is there anything I can do to change your mind?
So I love them both. You know, I really enjoy the planets that they visit and all the things they have in common there. I like the philosophy of Star Trek a little bit better than the swashbuckling Star Wars. But I think you've given it away. What about you, Jacob? Star Wars versus Star Trek? Yeah, I would pick
Star Wars. It's really just the lightsabers. They've got me. I want to do cool sword fights.
Yeah, it's pretty cool.
If you could have dinner with any astronomer or space pioneer who you haven't already met, who would it be?
I think I would pick Carl Sagan. You know, I think he was such a great scientist and a science communicator, and his creativity allowed us to do things as a human species that would have happened without him. And I think about, we did the episode about Voyager and the record that's on Voyager that has the sounds of Earth, including like the music of Chuck Berry, and just those moments of what human existence was like when that launched. That was his idea. And it's art in addition to being really amazing science. And so I would love to have a conversation with him about just his views of science and art and communication. It would be such a special dinner.
If you could go anywhere in the solar system safely and make it back, where would you go?
I think I would want to go closer to those moons around the giant planets.
Ooh.
Jupiter's moons, Saturn's moons, Titan, Enceladus, where we're finding these icy small bodies in our solar system that aren't planets on their own, but have conditions there that maybe could host life. I'd like to just check it out.
Yourself. Yeah.
Yeah. And what about you? Would you want to go out there or stay closer to home?
I would go to Venus, although it would take a heck of a spacesuit to keep me safe.
Yeah.
But, it's the planet most similar to Earth. And I'd love to find out how it ended up not similar to Earth.
What happened?
Right.
Yeah.
What did you do, Venus?
Very important question.
You're a singer. What's your go-to karaoke song?
Oh, so I like any Linda Ronstadt song.
Oh.
Yeah, so I'll go with You're No
You're
Good.
No Good. Yeah. Well, Padi, thank you so much for playing along. This has been super fun. All season, we've been asking listeners to send in their questions. Because even though there's a lot that we're curious about, we love it when you send us down the rabbit hole, too. And, we don't have time to answer every single question. But just like we promise, every season, we do our best to track down the answers to your questions from experts across NASA. So, Padi, I've got some questions. I'm going to tee them up, and I'm hoping you can help me answer these because you've got a lot more expertise than I do.
I'll do my best.
All right. If you're all set, the first question comes from Instagram from a user named RIZSFP. Are there many black holes in outer space?
There are many black holes in outer space. So we know two different basic size scales of black holes.
Okay.
Let's start the biggest ones.
Sure.
These are super massive black holes. Gotta love the words, right?
Yeah, well.
1 million times the mass of our sun, up to 1 billion times the mass of our sun. That's very massive.
Pretty massive.
Super massive.
Right.
And we now see supermassive black holes as being a key part of galaxy evolution. So virtually every galaxy out there that looks like a typical galaxy that you're used to, at the center is a supermassive black hole.
Okay.
Some of them are active. They're eating stuff around them. They're spewing energy out in jets. Some of them are quiet, like the supermassive black hole at the center of our galaxy. But we know it's there. We know there's supermassive black holes at the center of many, many galaxies, typical galaxies.
Okay.
That's a lot of galaxies.
That's a lot of galaxies.
Hundreds of billions of galaxies out there, so 100 billion supermassive black holes maybe.
Wow.
Then you talk about the small black holes. There are not as many massive stars out there as there are stars like our sun are smaller. So about 1 in 1,000 stars in our galaxy would end its life as a compact object, a stellar-sized black hole.
Okay.
And there's about 100 billion stars in our galaxy. And if 1 in 1,000 will end its life as a black hole, that's about 100 million black holes in the Milky Way, just the Milky Way, these small stellar mass black holes. But they're really hard to detect. So even though we've been looking for stellar mass black holes and we know that there are some out there and we've been studying them, we only know about a couple dozen at this point in time. We've discovered them, but we know the other ones are there from inferring what we know.
Wow. So that's a lot. So the answer is yes, there are many black holes.
So many black holes.
All right. Our second question is also sort of astrophysics related, so also sort of up your alley. It's also from Instagram, from a user named CodeQCode5280. And it's deceptively simple, I think. The question is, what is the speed of darkness?
What a cool question. I love the way that sounds. It sounds like it should be a movie or a song or an episode of the Curious Universe.
That's right.
Maybe. So speed of darkness is kind of, you have to put in the context of the speed of light. The speed of light is the fastest that anything can go. And darkness is the absence of light. So if darkness is us taking light away or light passing by, then the speed of darkness would be equivalent to the speed of light. But there are all kinds of thought experiments that can give you the illusion of darkness maybe moving faster than light. So you can imagine if there's a little, ant moving across a light source, and then if you were to think about its shadow that's further away, that shadow would look like the ant is moving faster. You'd see the shadow moving faster than the actual ant on the light source because it's being magnified, right?
Oh, okay.
Yeah, so it could give the illusion that it was moving a lot faster than it was.
Wow.
But in reality, nothing moves faster than the speed of light, even darkness.
Okay, a good answer. All right, well, our last question comes from a listener in Argentina who actually recorded an audio version of their question. So let's take a listen to this one.
Great.
Hi, my name is Gabriel Fuseli. I live in Santa Fe, Argentina. I'm a big fan of your podcast. I've been really curious about the universe since I was a child. So if I could ask to an astronaut and an astrophysicist, it would be, which are the procedures that astronauts must follow before and during a spacewalk? So thank you very much.
That's a great question. Thank you, Gabrielle, for your question. And as you know, a spacewalk is any activity that astronauts do in space when they're outside the spacecraft. And there are a lot of steps to properly suit up for a spacewalk. We checked in with an expert at the Johnson Space Center who told us something you might not know.
Which is?
Well, astronauts do something called in-suit light exercise, or ISLE.
Okay.
It's when they move their arms and legs around like a dance to purge their blood nitrogen. Did not know that. And this helps reduce decompression sickness when they go into the vacuum of space. Also, when on a spacewalk, astronauts have to climb aboard portable foot restraints. You turn a screw, your whole body will rotate in space. So these keep your feet stuck in place. And they might have 2 to 3 different work sites depending on what they're doing. Throughout the spacewalk, they'll often stop for spacesuit inspection, making sure their gloves aren't starting to get holes in them and that their helmets and the pads feel dry.
Wow. That little, I forgot what the acronym was, but the little dance you have to do to get the nitrogen out of your blood, it's something I never thought about, you know? Hearing what our listeners are curious about, I gotta say, is one of the best parts of working on this show because there's so many questions and so little time. But if you've been listening along, we'd love to know, if you could ask a NASA scientist or astronaut anything, I mean, like, dream big here. If you could ask them anything, what would it be? Well, you can send us your question to nasa-curiousuniverse@mail.nasa.gov, and we'll do our best to track down the answer. We may even get to answer your question in an upcoming episode. Here in our 6th season of Curious Universe, we went to some mind-blowing places, and this season had a few firsts for our team. For instance, we were able to travel out to Utah. Our producer, Christian Elliott, gathered on-the-ground recordings of the sample return of OSIRIS-REx. This was the first time that NASA collected a sample from an asteroid and brought it here to Earth. So let's take a listen from that episode.
All stations, we have visual on the SRC under the main chute.
We watched from mission operations as the surveillance plane cameras tracked the bright orange parachute through the blue sky. Then we lost sight of it as the capsule disappeared behind a hill. We couldn't tell if it was safe.
Oh, and it is touchdown.
All stations, we have visual confirmation of touchdown. However, it went behind a hill, so we do not have visual confirmation.
Mike and the other engineers and scientists were on the edge of their seats again. It took several minutes for the helicopters to fly across the huge ellipse.
Recovery operations, Helos 1 and 2 are in the area of the landing site.
But once they did, they could see the capsule sitting there with the parachute on the ground next to it, right next to a service road on a dry, flat patch of ground, just as the team had hoped. It was a perfect, gentle landing. Finally, everyone relaxed a bit.
SRC has been located.
Jacob, you and Christian were out there to support the OSIRIS-REx team's sample return. What was it like being on site during this historic NASA moment?
It was really cool to be there. And the moment that I'll never forget was after the capsule had landed, and we knew it was safe, and we knew that, you know, everyone was going to be happy and the science was going to be able to proceed. The capsule had actually landed in a spot that was off in the distance where we couldn't see. And so after that, the helicopters retrieving it just sort of appeared out of the mountains in the distance. And one of them had this long cable with a kind of basket thing that was carrying the capsule. And we saw it, again, just come out of the horizon, fly towards us, come right in front of us, and go to where they had set up a temporary clean room where the team could get to work. And even though there are people who've been working on this for something like 20 years, and I have not, I'm like, my involvement is so small, but I got goosebumps. I got chills just knowing that like pieces of outer space were right there in front of me. It was such a special moment to be a part of.
And seeing it with your own eyes, right? Like you know that it's doing okay, but just having that moment of visually confirming it.
And like you were talking about earlier, being with a team who's been working so hard to make it all possible, you really felt that camaraderie. Like, again, I didn't have anything to do with this, but I felt like, yeah, I did this. I was part of this, you know?
It's a moment for everyone, right? Yeah.
I can tell you about another episode that I've worked on that I have really enjoyed. And it was the focus of our season finale episode, which is called A Year in Mars Dune Alpha. So there are these 4 crew members. They're living in a simulated Mars habitat here on Earth. And NASA researchers are collecting data which will eventually inform how they'll plan an eventual human mission to Mars, like the real Mars, not a simulated habitat. So the crew is almost completely cut off from the outside world, but I was able to communicate with them by voice memo. So let's take a listen.
Hello, Earthlings.
This is what Mars airlock sounds like.
If I could sum up Chapia in just a couple of words, the words would be almost Mars.
People often ask what it smells like. It doesn't actually have a lot of smell, and one of the reasons is that most of the...
You hear a constant hum. I like to imagine it as the engine of Mars.
Science is an iterative process. You iterate on things, you make small discoveries that build and build. And I think that this study is an example of that.
Well, that is so cool. So did the voice memo process actually include like a delay, the same as you would have if you were talking to the folks on a Mars trip?
It did. So we expect that when people eventually go to Mars, depending on where Mars is in relation to Earth, there will be something like 15 to 20 minutes that it'll take a signal to go each way. So if you think about, if I'm on the crew on Mars and you're in mission control and I need to call you, I send you a message. It takes 15 to 20 minutes to get there. You figure out what you're going to say, and it takes another 15 to 20 minutes for me to get the answer.
Wow.
So the crew really has to be creative. They have to be problem solvers. And they also just have to exist in isolation with 3 other people and no sunlight and no fresh air for a year. And so for the researchers keeping an eye on these 4 crew members, there's a lot of valuable data that they can get from sort of how that all works and the impact it has on the crew members. So one other cool thing I want to spotlight is that we got to investigate the sounds of the sun. It's in an episode called Hum of the Sun, and we explain how heliophysicists, or sun scientists, are finding a lot of value in listening to our star. So one of the researchers discovered that the sun creates these harmonic frequencies that sound musical. And Patty, we actually get to hear you sing a little bit in that episode.
Yeah.
So let's listen. Here's what it sounded like.
When we get 2 regions that rotate together on opposite sides of the sun, we get an octave above that fundamental frequency. If we have 3 regions, they're now, if you kind of visualize it, they're equally spaced in thirds around the sun, and this creates an octave and a fifth. And above that we get 2 octaves, and then we get the major third and then the fifth. This creates these musical harmonic components in the solar wind. When you listen closely to the audio, you get this above the, you can hear the, and then depending on how much of the turbulent noise you filter out, you can hear the higher order harmonics. My mind was blown. It's like, you can hear the harmonic series in solar data. It's crazy.
So, Patty, when we, again, that's something to peel back the curtain a little bit. Listeners might not know that we basically surprised you with this and put you on the spot and played you this tape.
Yeah.
And then you just reacted spontaneously. So I was in the room when that happened.
Mm-hmm.
We were blown away by
Aw.
how it sounded in the end. But I'm really curious for you when you heard that
Yeah.
and sort of thought about what you could do with it. What was that like?
Well, I was so mind blown by the concept of being able to listen for patterns, right? Because we've been talking about looking for patterns. And now we're talking about taking the same data, but just putting it in through a different part of your brain. How does that part of your brain find patterns? And so music is all about these harmonics. How does like the fundamental and a third or a fifth relate to the whole sound?
Right.
I was just really kind of moved and blown away by the fact that we could hear patterns that were telling us something about what was going on physically, but also they sounded so beautiful and that we could just connect them to something that we're so familiar with. Music is very familiar to people, but it's invisible and it's mysterious, and we can't really measure the impact it has like on your soul or your feelings. So I just thought it was fantastic to think about how things sound.
Here at Curious Universe, as you know, we love to nerd out about space and all kinds of science. And by now, you have hopefully noticed that we also like to have fun while we do it. But I got to tell you, it wouldn't mean a thing if it weren't for you, the listeners. We really appreciate you listening, and we always love to hear what you think of the show. If you need a new adventure, you can always find us at nasa.gov/curiousuniverse. There's a backlog there of every episode we've released since 2020. And whether you're a first-time space explorer or a total space nerd, there's definitely a Curious Universe episode for you. All right, well, that's a wrap for Season 6 of NASA's Curious Universe. Again, thank you so much for tuning in this season and for supporting the show.
It's time for us to take a break and work on new episodes. But I promise we'll be back soon with more adventures. Until then, you can find us anytime at nasa.gov/curiousuniverse. And find even more NASA podcasts in your favorite podcast app or at nasa.gov/podcasts.
And remember, stay curious, and we'll see you next time. Thanks.